All right, let's talk about acid strengths for binary acids. Now, a little review. What is a binary acid?
Oh, I can't remember.
Well, do you remember the other kind?
Oxoacids, right?
Yep, there's binary and oxoacids. How do you know if an acid is an oxoacid?
It contains oxygen.
Okay, so a binary acid is an acid that contains only one other kind of element. Oxygen is an example, an oxoacid, H2SO4, for example, contains two different kinds of elements, but a binary acid would contain just one one other kind of element besides hydrogen, like HCl, HBr, right? H2S, right? So all of these are examples of binary acids, and they're named differently than oxoacids, right? Hydrochloric, hydrobromic, hydrosulfuric, sulfate goes to ic, sulfuric, so sulfuric acid, right? If you forgot how to name acids, you can go back and remember how to name those acids.
I remember I say it every morning. It goes to ic, it goes to us. It goes to it goes to ic, it goes to us. It goes to ic, it goes to us. It goes to ic, it goes to us. And then I read my Book of Mormon.
Very good, very good. Good job, Fred. You're a great student. All right, so acid strength increases, binary acid strength increases with what do you call that? Electronegativity. So the acid strength increases with electronegativity as you increase from left to right, but then it increases as you go from top to bottom. All right? So as you increase electronegativity from top to right, and we shouldn't say electronegativity because it's only for left to right, but then as you go down, acid strength actually increases. Now, we have to have a conversation about why something is a good acid, all right? And let's look at HCl. HCl is a good, strong acid, and when we say good, we're talking about the efficiency, how much it actually dissociates into the hydrogen ion and the chloride ion. And it's a strong acid because, and this is why all strong acids are strong acids, is because its conjugate base can be by itself in water. It can be very easily entertained by water very easily. All right? And that allows that H plus ion to come off and do its own thing. HCl is a good acid because the chloride ion is fairly large and lots of water molecules can get around it and can stabilize that chloride ion. HBr is actually a stronger acid because that bromide ion is larger, and therefore there's more space for water molecules to get around. What do you think? Is HI going to be stronger or weaker, Fred?
I think it'll be stronger.
That's right, it will be stronger. Now why? What's our explanation for that?
Because it's easier for water molecules to entertain it, therefore it's easy to separate from that hydrogen ion.
That's right. What about HF? Is HF a strong acid?
We didn't list it as a strong acid. I don't know.
HF is not a strong acid. In fact, if it does dissociate, it's it's a small amount. It only dissociates a small amount, and the reason is because it's small. Therefore, not a lot of water molecules can reach around it and convince it to leave its hydrogen ion, and so it attaches tightly to its hydrogen ion. Okay, so as you go across to the right, increasing electronegativity increases the strength of the acid. Fluorine likes to pull electron density toward itself, so HF, because of that, is stronger than the dissociation of water, for example, H2O. H2O can dissociate. That's kind of a secret that we're giving away at this point, but not really. We already said it was amphoteric, right? So H plus OH minus. This can occur, but it doesn't occur as much as HF dissociating, and that is again because the fluoride ion can stabilize that negative charge better because it has a higher electronegativity. HCl is a strong acid. H2S is not a strong acid. All right. So it's not hard to remember this information about the strength of binary acids because we know that these are the conjugate bases of the strong binary acids. Therefore, we remember that HF is not a strong acid. Therefore, this is an indication that acid strength is decreasing as you go up or increasing as you go down, right? Also, we can look at HCl and H2S and see that HCl is a stronger acid than H2S, and so we're increasing acid strength as we head to the left. Okay, good. So, which of these is a stronger acid? H2S or H2O?
Let me see the periodic table again. So HCl is stronger than HF, so H2S is stronger than HO.
Very good. That's right. How about this one? CH4 or NH3? Which of these is a stronger acid?
Those are acids?
Well, everything can be kind of thought of as an acid. And at some point, we always need to kind of consider things as acidic in terms of how much affinity that hydrogen has for the rest of its molecule. How easy will it be to remove that hydrogen from the rest of the molecule? These aren't acids, but which one of these would have an easier time releasing the hydrogen ion?
I guess CH4, right?
That's right. CH4 would be able to release that hydrogen more than NH3 because nitrogen is more electronegative than CH4. Okay, excellent. HF or HI, which one is a stronger acid?
HI is a strong acid.
That's right, HI is a strong acid. And why isn't HF included in the strong acid mix?
Because the fluoride ion is too small.
Very good. It can't be what?
Entertained by the water molecules very well.
All right, excellent. Oxoacids, their strength is almost entirely dependent on the electronegativity of the central atom. All right, and that's because for oxoacid, all the hydrogens are connected to the oxygens around the central atom. And so when they're all connected to the oxygens, the hydrogen, the decision that the hydrogen makes to leave that oxygen is dependent on the extra electron density that the central atom can donate or can take, right? Can take, actually, not donate, but take. Because, let's draw a picture of that. I mean, we have a picture drawn there, but let's talk through this picture. Central atom, like phosphorus, 4 oxygens, 1, 2, 3, 4, right? 3 of these oxygens have hydrogens on them. This one's double bonded. If hydrogen is going to leave, let's draw the dissociation in pictures. What's going to happen?
H leaves H plus?
That's right. Leaving behind what?
Behind the O minus.
That's right. It leaves behind an O minus there. So that O minus, just like in the binary acids, has to be stabilized. How can that O minus be stabilized? Well, some of that electron density will be taken by this phosphorus. And if that phosphorus is electronegative, so the higher the electronegativity, the stronger the acid this will be, because the more stable that negative charge can be once it's formed. So it forms the negative charge, the electron density can be managed by the phosphorus, and our strength of this acid is related to the electronegativity of the central atom. Another way that we can think about strength of acids is comparing the number of oxygens around the same central atom. So this PO3 with 3 hydrogens on it, right? This is the phosphite ion. or not phosphite, or it's the phosphite ion with three hydrogens on it there, so therefore it's phosphorus acid. Phosphite ion with 3 hydrogens, phosphorus acid. Phosphate ions with 3 hydrogens, phosphoric acid. All right, so phosphorus acid, phosphoric acid. Which one is stronger? Well, if I remove a hydrogen from here again, if I take this away, I'm going to be left with an oxygen with a negative charge. And that oxygen, that negative charge, needs to be drawn to that phosphorus. Well, another possible thing that that negative charge can do for either the phosphate or the phosphite ion is that negative electron density can swing over to this oxygen, and this oxygen can take the hydrogen. So it's kind of like a way of creating one of its resonance structures that can maintain electron density over here. And if you have more oxygens on the outside, you have more spots where that negative electron density can go. Therefore, you can stabilize that resulting negative charge easier. So if we have more oxygens, here's 2 acids, XO, H2XO2, H2XO3. The stronger acid is going to be the H2XO3 because with more oxygens, the resulting negative charge that's going to result when the hydrogen ion leaves will be more stabilized. Okay, so which is the stronger acid, H3PO4 or H3PO3?
We said more oxygens is stronger, right?
That's right, more oxygens is stronger because the resulting negative charge can be distributed around the molecule easier. How about H2SO4 and H3PO4?
Can you bring on the periodic table? I guess I don't need the periodic table because H2SO4 is a strong acid, right? But H3PO4 isn't.
That's right, but we can also use the periodic table and see how the electronegativity also is manifested there, right? Sulfur, the central atom on an oxyacid, is stronger than a central atom on an oxyacid, or when phosphorus is a central atom on oxyacid, right? And that's because of the electronegativity. Okay, how about this one? H3ASO4 or H3PO4? Same number of oxygens, arsenic and phosphorus. What do you think?
Which one is more? Phosphorus is more electronegative, right? Higher?
That's right.
So yeah, so I'd go with the phosphorus.
That's right. Very good. How about this one?
Let's see. Oh, more oxygen. So the selenic one, not the selenous.
That's right. Selenic acid, not selenous acid. Very good. Excellent. Okay, good place to stop. Good job.